Welcome to The Explainer. Today, we're going to completely flip how you look at chemistry. If you've ever felt totally bogged down by complex terms and, those confusing graphs when trying to learn about chemical energetics, well, I have some really great news for you. We're going to wipe the slate clean right now. Because chemical energetics isn't some pile of abstract jargon. It's actually just this fascinating, real-world story about energy moving around, changing form, and ultimately deciding what can and cannot happen in the physical world.
So, what if chemical reactions were literally just a game of energy bookkeeping? We usually think of chemical reactions as just, making new substances. But honestly, that's only half the picture. The real secret to understanding chemistry is to stop trying to memorize what things become and start tracking the hidden currency that actually makes the change possible. And that currency is energy.
There's this quote from the source material that I absolutely love. It says, "A reaction is not random energy magic. It is a trade." Think about pushing a really heavy object through a park. Sometimes you have to put your back into it and push that heavy object uphill, spending a ton of effort, before it can roll somewhere else. Other times, it just rolls downhill and gives that energy back to you in the form of momentum. Chemical reactions are just physical balances of energy, exactly like that.
All right, let's dive into Section 1, the hidden energy trade. Okay, we really need to bust a common myth right off the bat here. Bonds, they are not little physical hooks or sticks holding atoms together. They are simply low-energy, comfortable arrangements. So, breaking a bond forces the system into a way less comfortable state, which means it absolutely always costs energy. It's exactly like stretching a tight elastic band. Forming a new bond is like letting that band relax back into a stable shape, which, you guessed it, always releases energy. If you put this into a literal balance sheet, every single chemical reaction has to do two things. It must break old bonds, and it must make new ones. So it's always going to absorb energy, and it's always going to release energy. The whole secret to chemical energetics lies entirely in the final net result. The overall change just depends on which side of this ledger wins out.
Honestly, it's perfectly exactly like a shopping trip. When you go to the store to buy ingredients for dinner, you have to spend money. But later you get value back in the form of a warm, home-cooked meal. You wouldn't judge the success of your shopping trip just by looking at the money you spent, right? You have to compare the spending to the overall value you got back. In chemistry, breaking bonds is your upfront spending, and forming new ones is your payout.
And looking at it as a balance sheet completely demystifies where those tricky scientific terms come from. When the payout is bigger than the cost, meaning the energy released by the new bonds is greater than the energy it took to break the old ones, we call that overall profit exothermic. But when the upfront cost is higher than the payout, the system operates at a deficit, and we call it endothermic. See? There's no memorized magic here. It's just a simple balance.
So the crucial takeaway is that exothermic and endothermic simply describe the net direction of the energy flow, because energy never actually vanishes. Just like your phone battery doesn't magically destroy energy, it just converts chemical energy into light and heat. A chemical reaction just moves energy back and forth between the reacting system and its surroundings.
Which brings us to Section 2, the upfront investment.
Now you might be wondering, if an exothermic reaction releases all this energy overall and is super highly favorable, why doesn't it just happen instantly all on its own? Like, why isn't everything just constantly reacting all around us every single second?
Well, think about turning on a gas stove in your kitchen on a cold morning. You don't just get heat the second you turn the dial, right? You need a spark. That spark provides an initial energetic push. After that happens, the combustion releases way more energy than that tiny spark ever supplied. But without the spark, literally nothing happens, because those old gas and oxygen bonds are perfectly happy staying exactly as they are.
Chemists call that initial spark activation energy. It's the absolute minimum amount of energy required to just get the reaction moving. Remember our rule from earlier, breaking bonds costs energy? Before you can form those new, highly profitable bonds, you have to disrupt the old ones, which creates this messy, highly unstable temporary state. Activation energy is basically just the entry fee you have to pay to get into that state.
It's really absolutely crucial to emphasize a massive contrast here. Starting the reaction is a completely different question from the overall energy change. A reaction can release a massive amount of energy overall, but still have a totally huge upfront entry fee that makes it stubborn and slow to start. Activation energy is all about the hurdle. Exothermic or endothermic, that's just about the final balance.
Let's visualize this in Section 3, the invisible energy landscape. A chemical reaction is basically a journey through an energy landscape, sort of like a cyclist riding up and over a really steep hill. First, there's the starting state, pedaling on flat ground. Then, there's the highest energy point, that grueling, sweaty climb to the peak of the hill. And finally, there's the ending state, coasting down to wherever the journey finishes.
We can actually break this reaction profile down into a perfect 3-act story. The rising slope is the system absorbing energy just to loosen up those stubborn old bonds. The peak is that messy, unstable transition point we just talked about. And the falling slope, that is the reward. That's energy being released as the new bonds finally snap into place, bringing us down to the final energy level of the products.
When you compare these profiles, there's no guesswork at all. It makes it instantly clear. If the curve finishes lower than it started, the system gave away energy. Boom, that's exothermic. If the curve finishes higher than it started, the system absorbed energy into its final state. That's endothermic. The overall direction of the energy flow is just visually undeniable.
If you take away just one simple rule of thumb from this entire explainer, please let it be this. The peak represents the barrier, your startup cost. The endpoint represents the overall outcome, your final balance. Keep those two concepts totally distinct in your mind, and you'll be able to read literally any reaction graph like a professional. And why do these systems so often favor finishing lower? Because in chemistry, lower energy almost always means a more stable, comfortable arrangement. When molecules sit at a lower energy level, they are relaxed. They have way fewer energetic reasons to want to break apart and change all over again.
Let's tie the whole shebang together in Section 4, Thinking Like a Chemist.
There are 3 absolutely vital questions that form the true backbone of understanding chemical energetics. When a chemist looks at a reaction, they don't jump straight to the jargon. They ask, how big is that activation barrier? Does the final state end up being more or less stable than the start? And is the energy flowing out into the room as heat, or is it being sucked in? Because ultimately, chemistry is about paths, not just the start and end states. 2 completely different reactions might start and end at the exact same energy levels, for sure. But if one has a massive hill to climb in the middle and the other has just a tiny little bump, they are going to behave completely differently in the real world. The route the energy takes dictates everything.
This brings us to a beautifully simple summary from our source. Chemical energetics is the study of how energy moves, changes form, and shapes what reactions can do. By shifting your focus away from just the letters of the chemical elements and looking at the invisible flow of energy underneath them, you unlock the real actual mechanics of the universe.
So I'm going to leave you with a bit of a challenge. The next time you watch a fire burn or you see your phone battery tick down to 0, don't just look at the result. Ask yourself, what is the energy story here? What bonds are breaking? What was the upfront cost? And where is all that energy flowing? Thank you so much for exploring this with us, and keep looking for those hidden stories all around you.